Sharks are generally seen as the rough and tough ancient predators of our oceans. But did you know their skeletons are made of cartilage? That's right, the hit movie Jaws made you afraid of a creature that's made of the same material as what's in your ears. Well, maybe not entirely. The line traveling through the shark is its vertebral column, a backbone like yours, but made of cartilage. Like your backbone, theirs is comprised of individual vertebrae, however each is cylindrical in shape and has a unique internal mineral architecture. As you can see from the images on the slide, some sharks possess radiating spokes of mineralization called lamellae. This mineral architecture is found in lambda-form sharks, like mako, porbeagle, and white sharks, which are among the fastest fish in the oceans. Because fast sharks need to generate a lot of force to swim, these are good species for me to examine the relationships between mineral structure and function. Mineral arrangement has been shown to vary across shark species, and my work suggests it may also vary along the vertebral column. Previous experiments have shown that vertebrae closer to the tail are more likely to withstand deformation, or being squished, compared to vertebrae closer to the head. This means vertebrae nearer to the tail are more likely to withstand the strong forces needed for fast swimming. I believe the number and arrangement of lamellae impacts these mechanical properties and ultimately how sharks swim. To investigate this, I'm using a special machine called a micro-CT scanner to investigate 3 regions of vertebrae: anterior or closer to the head, middle, and posterior or closer to the tail. A micro-CT scanner is the same as a CAT scan that you would get at a doctor, just micro. The micro-CT scanner allows me to visualize the inside of the vertebrae and quantify the mineral architecture. Specifically, I'm examining the number of lamellae and how they are arranged within the vertebrae. As you can see from the sequence of images on the slide, the number of lamellae indeed varies along the vertebral column. These images are from a white shark specimen, and in comparison, mako and porbeagle sharks show a similar trend of higher lamellae counts in posterior regions. Now, what does this mean in terms of swimming? Well, posterior vertebrae are more stiff and more tough than anterior vertebrae, which means that they can withstand deformation and absorb more energy. Both of these mechanical properties allow for efficient energy transfer down the vertebral column, which is highest in the posterior region and where thrust is produced for swimming. We are also seeing the highest counts of lamellae in the posterior regions. Now, thinking outside the world of sharks, studying mineral architecture is important because it betters our understanding of biomechanics, composite materials, and cartilage in terms of human health. We are in the age of bio-inspired design, and today's research could impact better engineering materials or even advanced therapeutic strategies for calcified cartilage in your joints. So when you think about it, sharks aren't that scary. They're made of cartilage, and today's research could benefit your health in the long run. When you think about it, you could say that sharks have got your back.